Hello students, welcome to Untitled Classes. Now in this particular series we will learn about the mesomeric effect. So we will classify this or sort out this topic into around 8 to 7 subheadings, and the first one is over here, the pi bond conjugated to electron withdrawing group. Okay, now this would be known as the minus M effect. Okay, so for that, condition is that you have a pi bond and it is joined to a electron withdrawing group, and the electron withdrawing groups, they can be as follows, such as the NO2 group. You can also have the SO3H. You can have the carboxylic group, the ester group, the keto group. You can also have the aldehyde group or the cyano. Now, in all this, what is important is that the electron withdrawing group will be having itself a pi bond. At least one pi bond is there within it. Okay, so that is like a hint for you. Now, let us take some examples. Suppose we are discussing minus M effect. So let's take the nitro group. Now that means over here that this pi bond can be delocalized here, which can be further delocalized there, and that would generate the following resonance structure. Okay, since the group is pulling the electron density towards itself, so it is showing minus M effect. Similarly, say for the SO3H, one can think the electron withdrawing or withdrawal taking place in the following manner. Okay. Few more examples of the same kind. Okay, and it can go on and on. So I hope now it is clear to everybody that whenever you have a group that itself has a pi bond within it, it can pull the electron density towards itself. And one more thing is that the direction of pulling is towards the most electronegative atom, right? So this can be thought of. Now you can also extend the idea to groups when they are attached to the benzene ring. Okay, so out here one can think like this. There is an electron movement and the corresponding resonating structure is going to be as follows. And because of this electron withdrawal by the nitro group, a plus charge is being created at a position 2, which is also called the ortho position. Now if you think of generating another resonating structure, what you would find that the plus charge now comes to the para position with respect to the nitro group. And if you were to do one more structure, so eventually what you can conclude is that because of the nitro group being present on the benzene ring, some amount of residual positive charge is being created on the ortho and para positions, that is the 2, 4, 6 positions of the phenyl ring. Okay, so I hope now a similar thing can be thought of when a carboxylic acid group is attached to the benzene ring, this being the delta minus charge and this being the delta positive charge. तो ऐसे हम लोग फर्दर रेजोनेंस स्ट्रक्चर्स बना सकते हैं, और बाकी के मैं बना नहीं रहा हूँ, आप लोग बना लीजिएगा। एक और CN के लिए भी दिखा देते हैं कि उसमें क्या होगा। तो सिंपल सी बात यहाँ पे क्या है, जब भी कोई ग्रुप हो, चाहे वो कोई फिनाइल रिंग पे डायरेक्टली लगा हो या फिर कोई पाई बॉन्ड से कॉन्जुगेटेड हो और उस ग्रुप में पाई बॉन्ड हो, हाँ, तो वो अपने तरफ इलेक्ट्रॉन डेंसिटी को पुल कर सकता है, और पुल करने का डायरेक्शन क्या होगा, टुवर्ड्स द मोस्ट इलेक्ट्रोनेगेटिव एटम। इसमें जैसे कि बेंजोनाइट्राइल में नाइट्रोजन ज्यादा इलेक्ट्रोनेगेटिव एटम है, तो उसके तरफ इलेक्ट्रॉन की मूवमेंट होगी। ओके, और यहाँ पे भी सोचिए, अगर हमको फर्दर रेजोनेंस स्ट्रक्चर्स बनाना है तो पॉजिटिव साइड की तरफ इलेक्ट्रॉन की मूवमेंट होगी, पाई बॉन्ड की मूवमेंट होगी। तो इसी तरीके से हमें फर्दर रेजोनेंस स्ट्रक्चर्स जनरेट करने पड़ेंगे। ओके, एंड सो ऑन। बी पार्ट क्या है? When a pi bond is conjugated to a positively charged atom, okay? When pi bond is conjugated to a positively charged atom, मानो सिंपलेस्ट केस में क्या होगा, हमको अगर कोई एलाइल कार्बोकैटायन दे दे, ये क्या है, एलाइल कार्बोकैटायन। अब गौर करने वाली बात यह है कि यहाँ पे भी एक p ऑर्बिटल है, यहाँ पे भी एक p ऑर्बिटल और यहाँ पे भी एक p ऑर्बिटल, इसलिए कॉन्जुगेटेड सिस्टम है, राइट। तो अब इस कॉन्जुगेटेड सिस्टम में क्या होगा, अगर ये वाला पाई बॉन्ड इधर शिफ्ट होता है, पाई इलेक्ट्रॉन डेंसिटी पॉजिटिव की तरफ जाएगी, मैंने जैसे कहा डायरेक्शन ऑफ मूवमेंट ऐसे जज करेंगे हम लोग, तो ये हमारा फर्दर रेजोनेंसिंग स्ट्रक्चर होगा। तो इसी तरीके से हम ये भी सोच सकते हैं कि एक फिनाइल रिंग लेते हैं और इसके बगल में कार्बन रखते हैं जिसपे प्लस चार्ज हो। अब यहाँ पे भी इस कार्बोकैटायन के साथ ये वाला जो p ऑर्बिटल है ये सब कंजुगेटेड है, और हम सोच सकते हैं कि ये यूनिट यहाँ पे जो हमको मिल रहा है ये भी एक एलाइल कार्बोकैटायन के जैसा ही है। तो इसमें भी हम लोग अगर रेजोनेंस सोचेंगे तो हमारा नेक्स्ट रेजोनेटिंग स्ट्रक्चर जो है वो क्या होगा, वो कुछ इस तरह का होगा। और फिर हम मूवमेंट कराते हैं तो ये ऐसा, ये पॉजिटिव चार्ज यहाँ पे, और फिर अगर हम ये वाला चार्ज यहाँ मूव कराएंगे तो यहाँ पे पॉजिटिव चार्ज आएगा, और फाइनली ये वाला अगर ऐसा सोचे तो कुल मिला के हमारे पास इतने रेजोनेटिंग स्ट्रक्चर्स होंगे। ओके, नेक्स्ट केस क्या है, नंबर सी, व्हेन pi bond is conjugated to a neutral atom having empty p orbital। तो इसमें क्या हो सकता है, मतलब हाइपोवैलेंट एटम है, तो मान के चलो हमारे पास ये है। अब बोरॉन में क्या है, empty p ऑर्बिटल है क्योंकि वो हाइपोवैलेंट होता है, और यहाँ पे भी पाई ऑर्बिटल है और यहाँ पे भी p ऑर्बिटल है, तो इसमें कॉन्जुगेट सिस्टम हो गया। तो इसी हिसाब से अगर हम इसके लिए भी रेजोनेंस सोचेंगे तो ये क्या होगा, ये अपने तरफ इलेक्ट्रॉन डेंसिटी पुल कर रहा है, तो ये भी क्या दिखा रहा है, माइनस m इफेक्ट ही दिखा रहा है, राइट, इन दैट सेंस। तो यहाँ पे ये आपका हो जाएगा प्लस और ये हो जाएगा आपका माइनस, राइट। एक और एग्जांपल देख लेते हैं, अगर ये एग्जांपल हमारा 1 है तो 2 पे एक एग्जांपल और देख लेते हैं, वो क्या हो सकता है, मानो कोई NH ग्रुप हो और उसके बगल में BH2 हो, तो इसका जो लोन पेयर है यहाँ पे आ सकता है ऐसे करके, मतलब इसके जो MTP ऑर्बिटल उस पे आ सकता है, तो ये क्या हो जाएगा, N डबल बॉन्ड BH2 माइनस, और इस पे हो जाएगा प्लस, क्योंकि नाइट्रोजन हमारा क्वाड्रिवैलेंट हो जा रहा है। और क्या एग्जांपल्स हो सकते हैं, अगर ऐसा कोई सिस्टम सोच ले, तो इसमें भी मेरा BH2 ग्रुप क्या दिखा रहा है, माइनस m इफेक्ट दिखा रहा है, तो इसमें क्या होना है, इसमें भी हमारा p ऑर्बिटल है empty, ऐसे करके बोल सकते हैं। ये भी हमारा p ऑर्बिटल, यह भी हमारा p ऑर्बिटल, सो ये कॉन्जुगेटेड सिस्टम बन गया मेरा। तो यहाँ पे अगर इसको हम डोनेट करें तो इसमें आएगा नेगेटिव चार्ज और इसमें आएगा पॉजिटिव चार्ज। तो ऐसे करके हम दूसरा वाला रेजोनेटिंग स्ट्रक्चर बना लेंगे। तो मतलब यहाँ पे BH जो मेरा ग्रुप है वो भी मेरा -m इफेक्ट शो कर रहा है। अच्छा, अब D क्या हो सकता है? पाई बॉन्ड is conjugated to a pi bond। सिंपल सा सिस्टम है क्या, ब्यूटाडाइन। अब क्वेश्चन है क्या ये वाला ब्यूटाडाइन का ये वाला जो बॉन्ड है ये डबल बॉन्ड कैरेक्टर रखता है? तो अगर हम देखें कि इसमें अगर हम ये वाला रेजोनेटिंग स्ट्रक्चर को सोच करें, मतलब ये इलेक्ट्रॉन डेंसिटी ऐसा गया और ये यहाँ आया, तो इसमें तो आएगा प्लस और इसमें आ जाएगा माइनस। नाउ वी कैन सी दैट दिस पोर्शन इज हैविंग सम डबल बॉन्ड कैरेक्टर। सो यहाँ पे हम कह सकते हैं कि इन रियलिटी ब्यूटाडाइन का जो C3 और C2 कार्बन है उसके बीच में थोड़ा बहुत डबल बॉन्ड कैरेक्टर होगा। तो ऐसे सिस्टम को हम लोग कहेंगे क्या, कॉन्जुगेटेड सिस्टम। ओके, पहले तो ये समझ लें। अच्छा, ऐसा वाला सिस्टम अगर हमें मिल जाए तो ये हमारा हो जाएगा नॉन कॉन्जुगेटेड सिस्टम। ओके, और अगर ऐसा टाइप का कोई अलीन टाइप का सिस्टम हो तो इसको हम लोग कहेंगे, सॉरी, क्यूमुलेटिव डबल बॉन्ड्स। Okay, out of which only this one can undergo delocalization. Okay, that is what to be kept in mind. So some examples let's do. This and that is compared with this one and that one. So this is, we will say, a conjugated system. Non-conjugated. Okay. Now next topic, which is E. When a pi bond is attached to an atom having lone pair, which means you have a pi electron system joined to X. Suppose the X over here is halogen and it is having a lone pair. Alright. So X over here I am claiming it to be as halogen. So in those cases, the electron will be pushed towards the pi. Okay. So what will happen in that case? A plus charge will come on the X and the minus charge will come on the carbon. So let's take some examples of this. And one more thing to notice over here, whenever such a lone pair is conjugated, this lone pair should be sp2 hybridized. Okay, so this is one critical point that should be kept in mind. So suppose we have NH2, then such electron donation is possible, and whenever electron is donated towards the pi bond, we will show, or we will say that these are showing plus M effect or plus mesomeric effect. Okay, so say this is one, another one would be here too, donation is taking place. Okay, you can have a OR there too, donation is taking place. So these are all showing plus M effect. An interesting question that sometimes come, suppose you have been given as vinyl chloride and a simple ethyl chloride, and you are asked which of these bonds say this is A and this is B are shorter. So in that case, one has to remember, since there is a donation happening like that, so in case of a vinyl chloride, there is some amount of double bond character for the A, and so we will say these are shorter. In other words, A is shorter. A is shorter than B. Okay. On a similar note, if you compare the bond length of CCl presenting chlorobenzene with that of the cyclohexyl chloride, then here also since chlorine can show Plasm effect like this, so one can say that the CCl bond in chlorobenzene is shorter than CCl bond in cyclohexyl chloride. Okay. Next, when a pi bond is conjugated to a negatively charged atom, there also it will show Plasm effect. Okay, so here suppose we have this is called the allyl carbon ion, and that is how the electron donation happens. Okay, we can extend the idea to few more molecules. So this is your benzyl carbon ion. So this CH2 group is also over here showing Plasm effect. And it is increasing the electron density in the 2, 4 and 6 position of the benzene ring with respect to the CH2 group. As can be seen. Also important to notice that the negative charge moves towards the pi electron cloud, right? So if you compare this with the benzyl carbocation, you will see the reverse movement of the arrow. So here the negative charge is moving towards the pi electron cloud. Okay, and these are the following resonance structures that we will get. Mind you, we will do a separate lecture on only resonating structures, which ones contribute more or less. Okay, so we're not considering this over here, but we will do for sure. So this can also be extended to a system like phenoxide. So here also the O minus is showing Plasm effect, just like that. So just try to match whatever I have done for the benzyl carbanion and try to generate the other resonating structures over here, and that is how it should go on. Okay. Next topic, when the pi bond is conjugated to an atom having odd electron. So out here the simplest example that we can take will be the allyl radical. So out here what we have to think is that this bond is made up of 2 electrons like this. You take one electron using a half arrow, and you take one electron from using a half arrow and create a bond there. And for the other electron, we just put it here. So that way, if we think, our next radical structure will be like this. So this is how we can think of. Alright, in case of radicals. So these are the total cases that we wanted to discuss. Now out here, let us find out what is the mesomeric order, just like the inductive order. So in A we will have, and this is all dependent on electronegativity, okay. CH2 minus greater than NH minus, which is greater than O minus. So this is basically depending on electronegativity. In case of B, we will say an ionic species will be more electron donating than the neutral species. Suppose you considered amines, then amines attached to 2R will be more electron donating than amine attached to 1R, which will be more electron donating than amine attached to only H, which will be more electron donating than the amine which is attached itself to electron withdrawing group. Okay, and even more. So when it is attached to two electron withdrawing groups, it will be the least electron donating. Okay. In cases of halogens, if we compare fluorine with chlorine, with bromine, with iodine, this might be surprising for you, but over here, donation happens with respect to energy gap between the donor and the carbon. Donation happens with respect to energy gap between halogen and carbon atom, which means we mean to say that 2p energy gap is less than the 2p 3p. So that's why fluorine will be a better donor than that of the chlorine in terms of mesomeric effect. So this was the minus M effect order. What about the plus M effect order? So out here, suppose you are given a positively charged carbon, it will be more electron withdrawing than that of the neutral boron. So if you compare cyano group, it will be more electron withdrawing than the aldehyde, which will be more electron withdrawing than the ester, because in the ester itself there is some donation coming from the OR, okay, which will be more electron withdrawing than the amide. And that being the case, why? Because O is more electronegative than N, and so it is a less better donor. Okay, it is a less better donor than the NH2 group. Okay. Hello friends, welcome to Sarasa classes. Today we will learn rules for writing stable resonating structures. So in the first one, we will understand how the charges move. So we will say that negative charge, or if there is a lone pair, that will move towards a pi bond. And if there is a pi bond already, that will move towards a positive charge. Okay. Now let us understand this using some examples. Okay. So suppose we have something like this. So the negative charge moves and towards the pi bond, and so we will be getting the following resonating structures, or say we have something like that. Pi bond moves towards the positive charge and we get the following resonating structures. Okay, so this is what it means in the rule A. In rule B, we will say equivalent resonating structures will contribute more than the towards the actually the resonance hybrid, and will be more stable. Okay, what are the examples? Say we have been given the carboxylate ion. So if you look at the other resonating structure, then it is very similar to the first one, and both of these will be making an equal contribution towards the resonance hybrid, which will be having the following structure. Okay, or say let's consider the structure for a ozone. Then the resonance hybrid will be something like this, and both the structure 1 and structure 2 are making an equal contribution to the eventual resonance hybrid. In rule C, we will say stability of equivalent resonating structure is more than the stability of non-equivalent resonating structure, even though the later may have more resonating form. So what does this mean? Now let us consider acetate ion, and so we can say the other resonating structure will be as follows. And if you compare this with, say, a phenoxide, so in the above, both 1 and 2 are similar to each other. Okay, but in the phenoxide ion, if you compare structure of one with the other resonating structures, they are not equivalent. So they do not make an equal contribution to the eventual resonance hybrid. So as we can see, even though phenoxide ion may be having more resonating structures in comparison to the acetate ion, but in reality, the both acetate ions that you see are more stable and will be making more contribution towards the eventual hybrid, which is obviously the one shown over here. So not always true that if a particular structure may be having more resonating forms, so it will be the most stable one. If the forms are non-equivalent, then the eventual resonance hybrid will be less stable in comparison to the one which is having maybe lesser resonating structures, but all the resonance structures over there are of equal energy. ठीक है, नंबर डी पे चलते हैं. Neutral compounds are more stable than the charge separated resonating structures. In other words, polar structure is less stable than the non-polar structure. So for that, let us take an example of the 1,3-butadiene. In which we will say 1 is going to be more stable than the other resonating form 2. Each resonating structure must have same number of unpaired and paired electrons. So suppose we take an allyl radical, its resonating structure will be one that also has a radical. However, this one cannot be a resonating structure of the above allyl radical, okay, because there is one electron that is missing. Okay, in the next rule we will say position of atom cannot change in the resonating structure. Okay, so over here, in other words, we are saying tautomerism is not equal to resonance. So these two structures, as you can see over here, one which is a ketone and the other one is a enol, these two, they can be tautomers, but they cannot be resonating structures, because as you can see, the position of the hydrogen has changed. Next rule, we will say, if two resonating structures have same number of bonds, then that structure in which octet of every atom is complete, that structure is going to contribute more to the resonance hybrid. So for example, we take this one, and in the other structure we write in the following manner. As we can see now, here the carbon is having 6 electrons, but in this structure the carbon is having 8 electrons. So structure 2 is more stable as it has all the atoms in octet configuration than structure 1. In a similar manner, we can use another example in which so the lone pair on the oxygen will be donated towards the carbon, and as you can see in the second structure, all the atoms are having an octet configuration, hence again in comparison to structure 1 and structure 2 is going to be more stable. Okay, so this should be kept in mind. What is the other rule? Let me increase some space. In case of charged resonating structures, the most stable one is that in which the positive charge lies with most electropositive atom, and negative charge lies with most electronegative atom. Okay, so this can be understood by the following example. Suppose in one structure we have the negative charge on carbon, but on doing resonance we can see the charge to be shifting towards oxygen. So structure 2 will be more stable than structure 1. Okay. Again, we can take another example in which in this oxygen being most electronegative, negative charge will reside with oxygen and it will be more stable than in which the negative charge is on the sulfur, which is the less electronegative atom. Okay. What is the other rule? Resonance structures in which unlike charges are close, are more stable than when the charges, that is unlike charges, are far apart. What is the meaning of this? Let's take an example. Suppose we have taken a phenol. Now, the resonating structures that we will get are as follows. Now, if we name them, suppose this is 1, 2, 3, 4, and this is 5. We will say, obviously, as we have learned, that charged structures are less stable than the uncharged structures. So 1 and 5, these are of equal energy and more stable than 2, which is equal to 3. Sorry, 2 is equal to 4, and the least stable among this is 3, in which you can see the positive charge is lying far away from the negative charge. Okay. So when unlike charges are lying far apart, those structures are less stable. Next rule we will say resonance structures in which like charges are far apart are more stable than when they are close by. And that should complete the topic relating to the rules of resonance. Now we have been given some practice problems over here, and we have to apply these rules. So as we have studied that the lone pair will be moving towards the pi bond, so here the resonating structures that we will be getting over here is going to be as follows. The negative charge moves towards the pi bond, and so for the first one, the structures that we get are as shown. Out here, because of the minus M effect, the keto group will be pulling the electron density towards itself, and hence the resonating structures that we will get is as follows. Again, the same rule applies for the third molecule. Out here, okay, there's something wrong over here yeah, this is how it is, should be. So this goes in here, that goes there. Again, because of the minus M effect of the keto group, a positive charge will be created over here. Pi bond moves towards the positive charge, and so the resonating structures that we will get for the molecule number 3 is as shown. Again, the negative charge moves towards the pi bond, so that goes in here, and so this is the second resonating structure. Negative charge moves towards the pi bond, and hence these are the following resonating structures that we will get for this molecule. Again, the lone pair moves towards the pi bond, so out here this is the negative charge, which will again move towards the pi bond. So it means we will get the following resonating structures, which again moves in to give you the fourth resonating form. Okay. This is your acetatide, which I have done before, and so the structures that we will get is as shown. Negative charges, positive charges there, the pi bond moves in like that. For that, a positive charge will be created here. Again, the pi bond moves towards the positive charge. Hence, these are the following resonating structures that we will get. Again, this has been covered before. Negative charge moves towards the pi bond, and hence the nitro group will be having the following resonating structures as shown. Here there is a pi bond and there is a lone pair here, so the lone pair gets donated, the pi bond will eventually break, and the resonating structure that we will get will be as follows. There is a lone pair, so lone pair gets donated, okay, which means the pi bond electron breaks and comes here. So this is MEO plus, alright. The negative charge is over here, and this is the C triple bond N. Again, the negative charge moves towards the pi bond, and hence we will be getting the following resonating structures. Out here in guanidine, if this lone pair is donated, so this is the resonating structure we will obtain. However, the lone pair donation, if it happened from here, then the structure that we would have got would have been the following as shown over here. In this, over here, the negative charge can be donated in this side or in that side. So when it is donated towards the left hand side, this is the structure that we will obtain. If it is donated to the other side, that is the structure that we will obtain. Always the negative charge moves towards the pi bond. If we keep doing it, so this system is called the cyclopentadienyl anion. This is the negative charge that gets donated again. Charge moves in here, which gets donated again. That comes in, and we got to do this process till we get a system in which if we do the resonance, then it comes back to the original structure. Out here, again negative charge moves towards the pi bond. So we have this over here. Then this can go in here, and that will open up there. This can go in here. Another side that it could have gone is this side. Okay, so for that also we need to draw the resonating structures. Let's not forget that. So it could have gone either way, and if that went in here, then we would have got this structure. Okay, so these are the number of structures that we would have got for a carbonate ion. Just like the acetate or nitrate, bring it here, that opens up, this becomes double bond O. Instead of this, if had this one gone, then we would have got another resonating structure which would have looked the way I'm showing it right now. Okay, there are few more other structures which I am leaving it for you guys to practice. Okay, give it a try. Now the next one that we will do is to, this we are calling as in say part 2, and here we will do comparing the relative stability of following resonating structures. So let's create a table. We will say resonating structures, order of stability, and here we have suppose the reason for it. So let's have two such structures. We're calling this as 1. So its resonating structure obviously will be, now we're calling this as 1 and this as 2. So here 1 is more stable than that of 2 because the reason being charged resonating structure is less stable than neutral. Okay. Number 2, suppose we have these two structures. Now here 2 is more stable than 1, reason being negative charge in 2 lies on most electronegative atom. Three, again over here 2 is more stable than 1, and we will give the same argument as we had given for number 2. In this case, two is more stable than 1 because all atoms have octet. In question 5, we will say suppose we have been given this structure. One more stable than 2. Again, the same reason. Neutral structures are more stable than charged structures. In the following, one more stable than 2. In 1, we have all the atoms in octet, but as you can see, this carbon is not having octet configuration. In the following, all are of same energy. Stability and energy. In 8, here 1 is equal to 2. That means they are equivalent structures. In number 9, two is more stable than 1 because negative charge lies on the most electronegative atom. Okay. In number 10, two is more stable than 1 because all the atoms in 2 are having octet. Two is more or less stable than 1 because negative charge will be more stable on nitrogen. Two is more stable than 1 because negative charge is lying on the more electronegative oxygen. Okay. And so on. So I'm going to stop it over here regarding this, and I hope we have done sufficient examples to explain this particular section of the problem.